Now, let's combine all these ideas we've come up with about the work energy theorem in all the videos so far. So the work energy theorem tells us that the network will do what? It'll change our kinetic energy. It will also change our potential energy. It can also change our thermal energy. Okay? So this is a very generic expression about how work and energy are all related. Okay? But it also tells us that all the energy given to the system, the network that we do, splits up into other forms of energy. This is important. It's telling us that all the energy we have is conserved. Conservation of energy. Okay? Now we can play around with this formula and understand some different ideas. First, if we were to say, so if the system is isolated, okay, which basically means there is no external forces doing work on the system, okay, that means that our network is zero, the left side of that equation. Okay, so let's write that out. That means 0 is equal to the change in kinetic energy plus the change in potential energy plus the change in thermal energy. Now, recall that the triangle symbol means change, which is final minus initial. Okay, so that means I can separate all this. That the initial kinetic plus the initial potential is equal to the final kinetic plus the final potential plus our change in thermal energy. This expression is known as the conservation of energy in an isolated system. Okay? It's the exact same expression as the first one on this page, but we said it was isolated, so there's no network. Okay? So, if there are external forces doing work on the system, okay, so in other words, the system is not isolated, then we pretty much have the exact same expression, but we have this added quantity of network on the initial side. Okay. Now, we're going to quickly define another term here because we brought it up earlier, but we never actually defined it. When we take the sum of kinetic and potential energies, so we're not including network and we're not including thermal energy, okay, this sum, kinetic plus potential, and potential in any form, kinetic in any form, kinetic plus potentials, is defined as mechanical energy. Okay? So that means that if we have an isolated system, right, where the network is zero, and we have a frictionless system, that means that there is no change in thermal energy, then that means that all the mechanical energy must be conserved. Okay? Which we can write out as kinetic initial energy plus initial potential energy is equal to the final kinetic energy plus the final potential energy. All right, so kind of a lot there. But again, the idea is that energy is conserved. Whether if the system is not isolated, then any work we do, the network to add energy to the system, that means it's just going to redistribute into other forms. If we have an isolated system, then all the energy we have is just going to redistribute in other forms, and we could lose some as friction in the form of thermal energy. And if there's no friction, well, then all the mechanical energy is just conserved. It just transforms from one form to the other. Okay, and we're going to do a lot of practice with this because conservation of energy is a very important part of physics. All right, so we've established two types of potential energies, and each potential energy is a function of position. Okay? And there's other types of potential energies that we deal with in physics, just not in mechanics. But even those potential energies are in some way tied back to a position. So when we look at our two types, like gravitational potential energy, it depends on height, which is obviously the location between two positions. And then if we look at the elastic potential energy, this depends on the displacement of the string or the spring being stretched or compressed from equilibrium. So each potential energy is a function of position. So if we use that idea that potential energy is dependent on the position, what we then do is use energy diagrams to visualize the motion of objects through energy considerations. Okay. And so what we then do is when we make energy diagrams, it's essentially a plot of energies as functions of position. All right, so we're going to draw out an example, and then we're going to talk through the pieces that you'll see. All right, so let's start with a very basic graph. So we're going to have two axes. You're going to plot position on the x and potential energy on the y. So when you have a very generic curve, so I'll do this, we'll do this in red. Okay, the curve represents the potential energy as a function of position. Okay, so now let's make a second graph. And all we're going to do is keep adding to this graph. So I'm going to draw it separate times to add each piece. And you can draw it on the same if you want. I just didn't want to cram all the explanations into one graph. So we're going to copy this graph over and add another part. So I'm going to do this in a different color. We'll draw it in green. Okay, and our green line is a straight line at the highest point on the graph. This represents our mechanical energy, which, as we know, is conserved. So however much total energy we have, we'll never lose any of this. And that's why it's a straight horizontal line on our energy diagram. So remember, mechanical energy is the sum of kinetic and potentials. Okay, now the last component is not necessarily drawn on the graph, but it's important to understand where it's coming from on the graph. So we'll make another copy, and we're going to add in a piece. I'll do this in a different color. We'll do it in, say, blue. And if we look at the distance between our total energy line, the green line, and our red line, okay, this distance between them on the graph is actually our kinetic energy. Okay, so the green total energy line is our highest point on the graph. The red line is our potential energy. So however high up the red line is from our x-axis, that's how much potential energy we have. So that remaining portion from the red to the green represents the kinetic energy. Okay, and graphically, that's what it is. And if we look at it mathematically, at the previous statement about what the total mechanical energy is, if we solve it for kinetic energy, we get total mechanical minus the potential. So total being the green line minus where the red line is, and that extra space tells you how much kinetic energy you have, which should make sense. If you follow the red line, the closer I get to the total mechanical energy line, the less potential, or excuse me, the more potential I get and the less kinetic we have, because there's less space. Okay, so let's do kind of a quick visual example. So for this, we're just going to look at a ball being thrown upwards, and just to give you an idea how this will work. Okay, so we're going to start with the ball on the ground, but we're throwing it upwards with a velocity. Okay, so if we were to plot this, let's put that it's on the ground, kind of signify that. Okay, so it's at a height of 0. So if it's starting out at 0 and we make a potential energy diagram or an energy diagram, the total mechanical energy is represented by our line, which if we had scales we would number it something, but this initial point is at 0, 0. The height is 0 and there is no potential energy. And the space between that dot and the total energy line, EM, is our kinetic energy, which should make sense. As we're throwing the ball up from the ground, all it has is kinetic energy. Now, sometime later, the ball's a little bit above the ground. It's got a little less velocity because gravity's slowing it down, but it's getting higher off the ground, which means our potential energy should be increasing. So again, we got our total energy line, and we have 2 points to plot here. Okay, so you'll notice that this line is getting closer to the total energy line. And since this line is getting closer, that means we are losing kinetic energy and gaining potential, which should make sense. The object's moving up, so we're gaining potential, but as it's moving up, it's slowing down, so we're also losing kinetic. Okay, and then in the final picture, so sometime later, the ball is now at its highest point, which means it has no more velocity, and after this, it's going to start to fall. So at this moment, there is no velocity, and if we plot this on the energy diagram, that would mean that all the kinetic energy has transformed into potential energy. So if we plot our 2 points from the previous 2 parts, and then add in a third point for this, the third point should be right on the total energy line. Okay, because when it's on the total energy line, all the potential energy has, or all the kinetic energy has been transformed into all potential energy, which now represents the total energy of our system. Okay. So that's the kind of the basic idea of how these diagrams are made. Now, when you use them, it's not going to be so much of plotting the points from an object. It's going to be more about the functions. So we have to understand a little bit more about the diagram. So let's do another one. So again, we have this is an arbitrary graph of energy. So we mark off our total energy line, and then we draw a simple curve representing the potential energy of some object. Okay, so now you'll notice that there should be, or you should identify that there's a problem here. If you look at this small segment of line above the total energy line, why is this a problem? The answer is you can't do this. How does an object gain more potential than the total energy it had to begin with? Where did this extra energy come from? So if the curve goes above the total energy line, this could mean this means two things, excuse me. It means the gravitational potential energy is greater than the total energy. Well, that doesn't make sense. But it also means that the kinetic energy is negative.
Well, each of these is not likely. Let's look at the first one. So why can't the gravitational energy be greater than total energy? Okay, now the only way this could be possible is if there's some net external work done on the system. Okay, if we do some extra work when it reaches this position, then we will obviously add energy, but that means we have to raise our energy line. But when we look at when kinetic energy is less than 0, well, this is physically impossible. Right? Kinetic energy is 1/2 mv squared. The only number in there that could be negative is the velocity, but you're squaring it. So how are you going to get a negative kinetic energy? So let me add this point in. If you did external work on the system, you can satisfy that the gravity potential energy got higher than total EM, because what you effectively did is there was work on the system which added energy to the total energy of the system. So when that happens, we would erase that straight total mechanical energy line, and we would raise it up so that the curve is still underneath that line, simply because we added energy to the system. Okay, let's look at a couple other things about an energy graph that's going to be important. Now from here, we're going to actually start drifting into some calculus knowledge. So those of you in AP Calculus will hopefully be able to connect the dots, and those of you that are not, hopefully the physics makes sense. So we're going to look at an energy diagram, total energy line, and we're going to have a curve. So just a random curve, and we'll do this one in red like we did before. Okay, so now there's 2 points of interest on this graph. Now those points are where the graph turns. So we got 2 of them here. Okay? So they're known as turning points or equilibrium points. Now, what does that mean? So there's 2 different kinds. One's like a hill, and one's like a little valley, if you will. So let's name. We'll label those. We'll say point 1 and or point A and point B. And so let's look at point A. So point A is known as an unstable equilibrium point. Okay. Now, one of the easiest ways that I like to think of what makes it unstable and stable, or how to know it's unstable or stable, is imagine that that was like a hill that you were to put a marble on. Okay. Now there exists some point on that hill where the marble would be at rest. It would be in equilibrium. But if I nudge it just a little bit in any direction, it's going to immediately roll off the other side and will never come back. Okay. Or at least there will be some additional work required to bring it back. Okay. So I look at the unstable equilibrium as a point where things can come to rest, but then they'll start to fall again. So like that would be a ball being thrown up in the air. It hits an equilibrium point when it's at the max height, but then it starts to fall back down. Okay, the next is a stable equilibrium point at B. And if we use the marble analogy again, there exists a point below, on the bottom of that valley, where the marble would be at rest. Now if you were to nudge it in any direction with a force, all that marble is going to do is roll slightly up one side, and then it'll come back down. And it might go back and forth a little bit until eventually it comes back to rest at the bottom of that bowl, if you will. So I call that's stable equilibrium, because even if I nudge it, it'll eventually return to that point. All right, now an example of stable equilibrium would be a spring. Okay, no matter how much I compress or pull on that spring to either push it in or stretch it out, it will always try to return back to that equilibrium. Okay? So when the thing wants to return to equilibrium, it's stable. When it's in equilibrium, but at any moment it could move away from equilibrium, then it's considered unstable.